5 minutes to show you a soft robotic tentacle powered by high-performance, self-sensing artificial muscles. This innovation doesn't just solve the preloading headache associated with traditional artificial muscles, it effectively implants nerves directly into them, achieving millimeter-level control precision across a wide range of motion. So, how exactly is this powerful performance achieved? Let's dive in and find out. Let's look at the robot's heart, its core driver, the twisted and coiled actuator, or TCA for short, commonly known as artificial muscle. If you've worked with soft robotics, you might know that while TCAs offer high energy density, they come with a major flaw. They usually require preloading. Simply put, you have to stretch them tightly before they work. This is a hassle for soft robots because that tension can deform the soft materials. To solve this, the research team improved the manufacturing process by introducing controlled initial gaps. Think of it like leaving space in a spring, so it can contract electrically even from a completely relaxed state. No external stretching required, making it a perfect fit for soft structures. Plus, they wrapped nickel wire within the traditional nylon threads. By tracking the change in resistance of the nickel wire, the muscle can sense its own temperature with extremely low error. To evaluate how much deformation influences the resistance compared to temperature, the researchers conducted the experiment shown in Figure A. The result is quite surprising. The resistance change caused by temperature is more than 60 times larger than the change caused by deformation. In other words, the mechanical stretching of the wire has only a minimal effect. So for this nickel wire, the contribution of deformation to resistance can essentially be ignored. By fitting the experimental data from the nickel wire's temperature resistance tests, the authors derived a clear relationship between resistance R and temperature T. They then validated this model inside an oven. Across the typical operating temperature range, the average measurement error was just 1.82%, and the maximum error stayed below 6%. It's essentially a smart muscle that is both strong and sensitive. Now that we have powerful muscles, the next step is assembling them into an arm and giving it skin, essentially, its structural integration and sensing system. The team created a silicone soft body for the arm, with 3 TCA artificial muscles arranged at 120-degree intervals around the central axis. But how does the robot know how much it has bent while moving? It relies on optical fiber macro bend sensors embedded in the surface grooves. The principle is simple. When the fiber bends, light is lost. By measuring changes in light intensity, the system can calculate the bending angle. The team buried 3 such fibers around the tentacle, creating the robot's proprioception. Now, what about tactile sensing, the feeling of touch? They installed a stretchable optical waveguide tactile sensor at the tip of the tentacle. It's a soft cylinder where the light signal changes when pressed. This effectively gives the robot a sensitive, tactile fingertip. The hardware is ready, but here comes the biggest headache in artificial muscle-driven soft robotics. Control is difficult. This requires a smart brain. The research team designed a multi-input, multi-output, MIMO, closed-loop controller to serve as that brain. This system operates on 3 layers of logic. The first layer is a neural network, which accurately translates optical signals into position coordinates. The second layer is feed-forward compensation. Think of this like anticipating where a ball will land and reaching out early. It drastically improves response speed. The third layer is PID control, used for real-time fine-tuning. Let's check out how this feeling tentacle performs in real-world tasks. First up is the drawing test, to evaluate its control precision. In the trajectory tracking experiment, this robotic arm proves to be quite the artist. Researchers tasked it with drawing circles, hexagons, and even Archimedean spirals. As you can see, Whether it's a smooth circle or a sharp-cornered hexagon, it tracks the path very tightly. Specifically, in the hexagon repeatability test, the mean absolute error was only 0.49 millimeters. For a soft robot driven by heat, that level of precision is remarkably impressive. Next is the tactile test, you're likely most curious about. Does it really have skin? As we mentioned, it's equipped with an optical waveguide tactile sensor. In the experiment, researchers made the tentacle bend down to touch objects of different materials, such as sponges and silicone blocks of varying hardness. Through signal differences, it can accurately distinguish between soft and hard. But that's not all. It can also perform press detection and surface recognition. When you continuously press on its surface, it senses the change in force in real time. When it slides across different surfaces, combined with the neural network, it can distinguish whether the road is flat or wavy. It's just like a human touching something with their eyes closed, knowing not only what it touched, but also the texture of the surface. Finally, here comes the fun part: dynamic tracking of a yellow rubber duck. They mounted a camera on the tip of the tentacle to track a moving duck. You can see that no matter how the duck moves, the tentacle flexibly twists its body to keep the duck locked in the center of its field of view. This proves that it can do more than just follow a preset trajectory. It can combine vision and touch to respond to external changes in real time. Although it is currently just a single tentacle, imagine this: if we link multiple modules like this together, could we build a robotic arm that is as flexible, powerful, and precise as an octopus tentacle? This offers a very promising direction for future medical surgical robots or exploration in complex environments.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.